try to share my slides. Okay, okay. So for tonight, we will be discussing about permeability and seepage. Okay. So I'm now sharing my slides, so I hope everyone can see them. Okay. And I hope I'm also clear with everyone. Okay. So again, if you have some issues with the presentation, please call my attention as soon as possible, or you can just simply type in the chat box. Okay. Okay. So again, soils are permeable. Okay. So soils are permeable due to the existence of the interconnected voids, okay, through which water can flow from points of high energy to points of low energy. Okay. So again, the study of the flow of water through a permeable soil media is quite important in soil mechanics. Okay. So again, when we talk of permeability and seepage, that means that your voids must be interconnected. So if there is no interconnection of the voids between the soil particles, then there is no permeability or seepage that can occur. Okay. Now, it is necessary for estimating the quantity of underground seepage under various hydraulic conditions for investigating problems such as the pumping of water for underground construction. Okay, this we normally do in construction projects, especially if the groundwater level or the groundwater table, okay, is higher than your excavation depth. Okay, so normally we pump out water. No? Normally we do the sump and pump. No? We create a sump pit and then we put there some pumps. Then we try to extract the water, no? So that the excavation embedment level will become dry. So then we can start constructing our foundations, for example. No? Then after we pour the concrete into the foundations, and then we start to do the backfilling works. Okay. Then we can now start to pull out the pumps and then yeah. As long as you're already above the level of the presupposed groundwater level. Okay. Then we can work our way up. Okay. Until the ground level. Okay? Um, Yeah, I recall that I think 10 years ago we had a project where we were excavating about 20 meters by 30 meters depth. Okay, and then at around this is about 12 meters of excavation. So you can just imagine the volume of earthworks there. That's 20 by 30 by 12 meters deep. Okay, then at around 7 meters depth water started gushing out uh, from the through the excavation. Okay, then the whole area became a swimming pool. No? Okay. And aside from that, we also do stability analysis of earth dams, okay, and earth retaining structures that are subject to seepage forces. Okay. Although in practice, you can do this by hand, but in practice, we use already commercial softwares in doing seepage analysis, especially with respect to um, excavation protections. okay, or stability analysis no, of earth dams and earth retaining structures. Okay. Later on, I'll show you an example of that one. Okay. So one of the major physical parameters of a soil that controls the rate of seepage, okay, the amount of water flowing through, okay, that's the seepage. Okay, so the physical parameter is what we call the hydraulic conductivity. Okay, yeah. That's uh, the that's how fast the water would flow into the ground. Okay. Now, another term for hydraulic conductivity is also called a coefficient of permeability. Okay, so basically these two terms are just relatively the same. Okay. Okay. Now, from fluid mechanics, not sure if you already had that subject. Okay. Now, from fluid mechanics, we know that according to Bernoulli's equation, okay, the total head, okay, not minding yet, not the ground, uh, the total head at a point in water under motion can be given by the sum of three terms or three um, parameters. Okay, it should be the sum of the pressure, the velocity, and the elevation heads. Okay, in such a way that the total head, okay, H, okay, is now equal to the pressure head. Okay, the pressure head. I hope you're seeing my cursor. The pressure head, the velocity head, and the elevation head. Okay. So the pressure head is equal to the pressure over the unit weight of water. And then the velocity head is equal to the velocity squared over 2 times the acceleration due to gravity. Okay. Then plus the elevation head. So again, we take note. Okay. So again, if you have the book, I just copied this from the book. So if you have the book yourself, okay, you can just refer to your book as well. If you have difficulty in my presentation. Okay. So I'm just practically going through the book. Yes, as I speak. So here we have to take note that the elevation Z, the elevation head Z, is the vertical distance of a given point above or below a certain datum plane. Okay, for example, when we talk of ground elevations, no, when you did your surveying, okay, your subject in surveying, normally the field ground elevations is the day we base our datum plane from the sea level. Okay, that's our datum plane. Okay. Okay. Now, if Bernoulli's equation is applied to the flow of water through a porous soil medium, okay, so when you say porous, that means that the voids are interconnected, okay, with each other, okay, in such a way that water can flow easily within the soil particles. Okay. In this condition, if we apply the Bernoulli's equation given in equation 7.1, I'm not sure if it's still the same equation number in your book. Okay. Now, in that equation, the term containing the velocity head, okay, this one here, can be neglected, okay, because the seepage velocity, talking of ground, no? Talking of um, ground conditions, okay, the seepage velocity is quite small, okay, in such a way that we can practically neglect it. No? We can neglect the velocity head. Unlike in fluid mechanics, wherein you have the um, okay, the water velocity within the pipes, no, for example, which is quite fast. No? You cannot neglect it. But in ground, in the ground, as far as the Bernoulli equation is concerned, um, then we can probably neglect the velocity head. Okay, so in that case, the total head at any point can be adequately represented by equation 7.2, wherein the total head is now just equal to the pressure head. Okay, um, So if you're now talking of the ground, then this is now the poor water pressure head. Okay. Yeah. Over the unit weight of water plus the elevation head. Okay. So this figure here, okay, this figure here shows the relationship among the pressure, the elevation, and the total heads for the flow of water through the soil. Okay. Yeah. So if you look at this figure here, okay. So we now have here, for example, if this is now your medium, okay, your soil medium, and then this is now the flow of water into the soil medium. Okay. Then if we have, okay, if we have, or if we put open standpipes, for example, which we can call piezometers, okay, or piezometers, okay, are installed at points A and B. Where's the point A and B? Okay, so if this is now your point A and this is now your point B, okay, for example, you put here a piezometer, okay, this one here, okay. Although in actual practice, this is now what we call the boreholes, okay, in geotechnical investigation. So we drill boreholes into the ground, and then water will start to rise up in the boreholes, no? And then we try to measure them, okay, to check the groundwater levels. So in this case, this is now your groundwater levels. Okay. Yeah. So the levels to which in the piezometer tubes or the piezometer tubes situated at points A and B, okay, are known as the piezometric levels. Okay, we call them the piezometric levels at points A and B respectively. Okay, so that means that the point A, if water here will rise, then this is now the piezometric level at point A, and then this one now is the piezometric level at point B. Okay. So the pressure head at a point is defined as the height of the vertical column of water in the piezometer installed at that point. Okay. Yeah. So here we can see the okay the for example at point A. Okay. So this is now the pressure head. Okay. At from point A until the piezometric level. So this is now your pressure, poor water pressure head at point A. Whereas this is also the poor water pressure head at point B. Okay, so that's U sub B over the unit weight of water. This one here is the um, poor water pressure at A over the unit weight of water. That will give us the pressure head. Yeah. Okay. Okay. Now, now at these points A and B, if we now try to refer to the datum, okay, which can be the sea level, no? Okay, the mean sea level, for example, in the actual field, okay, then from this point until the datum, we now call it the elevation head A, and then from this point until the datum plane, we now call this your elevation head B, in such a way that the pore water pressure head plus the elevation head will now give you the total head from the datum plane. Okay. Same for B, you now have here the pore water pressure head plus the elevation head. Okay, will give you now the total head from the datum plane. Okay, so again, don't worry about this picture. I just took them from the book. Okay, so you can just refer to your book as well. Okay. Now, the loss of head between 2 points, A and B, can be given by this one here. Okay, so this is now the delta H or the delta H or the head loss. Okay, is now equal to the total head at A minus the total head at B. Okay, so if you look at the figure here, so we now have the total head at A minus the total head at B will now give us the head loss. Okay, yeah. So that means this is now the loss of head um, uh, from point A to point B. Okay, so that means if you can find here the piezometric level at this point, okay, and then here you have the piezometric level at point B. And if there's now a head loss, then we can see here that the flow of water is from this level to this level. So that's why the flow of water is in this direction. Just like in actual practice, when we try to drill, for example, 10 boreholes in a certain project, okay, then normally we measure all the groundwater levels in each borehole, okay, and then we try to compare them, and then we can probably see the general direction of the groundwater flow by just looking at the groundwater levels. So we don't normally expect the same groundwater level readings for all the 10 boreholes in the field, for example. So there can probably be a trend, okay? Because if all the groundwater levels, for example, in the 10 boreholes that we do, if the groundwater levels in the measurement, when we measure in the boreholes, if they're all the same, then that means I will not expect any groundwater flow. For example, he said that means the groundwater level is static. Okay? There's no ground water flow movement. Okay. Okay. Now, so the head loss or delta H no, can be expressed in a non-dimensional form because the head loss here is say it can be in meters in terms of length. Okay. So if we can express it in a non-dimensional form, okay, where it now becomes where we now have I is now equal to the head loss over the length L, or that's now the distance. The length L is now the distance between the two points. It's not the horizontal distance, but rather it is the distance along the direction of the flow. Okay, that's now your length L. So with that, then we now have I, which is now the hydraulic gradient. Okay? We now call it the hydraulic gradient. Is now equal to the head loss over the distance between points A and B. Okay, so again, that's the length of the flow over which the loss of head occurred. Okay. So please take note of these equations, no? Because later on we will be using them in deriving other equations. So this will now serve as your basic equation. Okay. So in general, the variation of the velocity v, small v, with the hydraulic gradient I, which we just have defined here, okay, can be shown in this figure. Okay, that's figure 7.2 in your book if you're using the same edition. Okay, so that figure is actually divided into three zones. Okay, so we have the laminar flow zone, that's zone one, the transition zone, that's zone two, and then we have the turbulent flow zone, that is zone three. Okay. So here, if we now have the relationship between the hydraulic gradient I and the velocity v, okay, yeah. Then from this point until this boundary, then here we still have a laminar flow in such a way that we still have a linear relationship between the hydraulic gradient and the velocity. Okay. Then here, this is now the transition zone between this boundary and this one here. Okay, wherein this is now the transition zone between the laminar flow zone and the turbulent flow zone. Okay, yeah. So when we say laminar flow zone, that means you can probably visualize this like a uh, a very calm um, creek, for example, that is flowing. Okay, that's laminar flow. Okay, so when we say turbulent flow zone, then you can imagine this rivers, no, wherein you have rocks and so on and so forth, wherein you have a turbulent flow. Okay, so that's now zone three. Okay, now when the hydraulic gradient is increased gradually, okay, so this one here, when the hydraulic gradient is increased gradually, so the flow remains laminar in zones 1 and 2, and then the velocity v bears a linear relationship to the hydraulic gradient. Okay. Now, at a higher hydraulic gradient, the flow becomes turbulent. No? That's zone 3. Okay. Now, when the hydraulic gradient is decreased, okay, then we now have the laminar flow conditions which exist only in zone 1. Okay. Now, in most soils, the flow of water through the void spaces can be considered laminar. No? So, okay, so this one here. Okay, so with respect to the ground, then we can assume that it is following a laminar flow. Okay, this one here. So therefore, we can have a linear relationship between the velocity and the hydraulic gradient. This is the symbol for directly proportional. Okay. Now, but in the case of a fractured rock, stones or gravels and very coarse sands, then turbulent flow conditions may exist, and this equation here may not be valid. Okay, so maybe it is just applicable to fine sands and below. Okay, not uh, not this one here. Okay, not this um, ground conditions. Okay, okay. Now, with respect to this proportionality equation here, Darcy in 1856 published a simple equation for the discharge velocity of water through a saturated source. Now, take note, Darcy was testing saturated source. Okay, so he was not doing experiments on or in unsaturated soils, okay, or partially saturated soils. Okay, so that means this equation here, please take note, okay, this is only applicable to saturated soil conditions. Okay, because in the masteral degree, for example, when we discuss unsaturated soil mechanics, then we add here another parameter to describe the discharge velocity of water in the case of unsaturated soils. Okay. Now, for the moment, let's stick to saturated soil conditions. Um, that means the soils here are below the groundwater level. Because above the groundwater level, that's already under the realm of unsaturated soil mechanics, which I also teach in the master's degree. Okay. Now, I think we learned from a ratio and proportion. Okay, that if we have the proportionality constant, and then we replace this by an equal sign, okay, then we have to introduce a proportionality constant. Okay, so that's why here in this equation, if we want now to relate the discharge velocity, okay, within the pores of the soils, okay, then if we equate the discharge velocity to the hydraulic gradient, okay, so again, if you recall, the hydraulic gradient is the ratio of the head loss um, over the length to which the head loss has occurred. Okay. So with this, so V here is the discharge velocity, which is now the quantity of water flowing in time, in unit time, okay, through a unit gross cross-sectional area of soil at right angles to the direction of flow. Okay? And then a K here is now what we call the hydraulic conductivity, or otherwise known as the coefficient of permeability. No? Okay, so these two terms are just the same. Okay. Yeah. Okay. So this equation, okay, is based primarily on Darcy's observation about the flow of water through clean sands. Okay, through clean sands. Okay, so that means it only has a minor percentage of fine content. Huh? Okay, fines. Okay, so this equation here, equation 7.6 and equation 7.5, again, take note, they are both valid for laminar flow conditions and is applicable for a wide range of soils. Okay, okay. So again, in this equation here, okay, so the discharge velocity of water based on the gross cross-sectional area of the soil. Okay, that's now your V. Okay. However, the actual velocity of water, which is now what we call the seepage velocity, okay, it's not the same as the discharge velocity, um, through the void spaces, okay, would be greater than the discharge velocity. Okay. Now, when you talk of fluid mechanics or when you talk of hydraulics, okay, then you have the discharge velocity for your pipes. No? Okay, but here in the ground, aside from the discharge velocity, there's also what we call as the seepage velocity. Okay. Now, the relationship between the discharge velocity and the seepage velocity uh, can be can be derived using this figure here. Okay, yeah, wherein you now have here your specimen, for example, your soil specimen. Okay, yeah, and then it's uh, flowing through an area of soil specimen, okay, which is now your A. So in this case, um, everything is completely filled with um, water, no? In this case, okay, yeah. But in this case here, we can also represent this one here, okay, with two sections, okay, wherein you have this one here as the area of the soil solids, okay, in the cross section, which is now A sub S, and then this one here is now the area of void in the cross section. That's A sub V, okay, where the flow rate Q is flowing through in a particular length, L, no, along the soil specimen. Okay. Okay. So with that, so if the quantity of water flowing through the soil in unit time is Q, okay, so this one here, okay, this is now your quantity of water flowing. Okay, so that's or rather that's also called the flow rate. Okay, the flow rate. Okay, so that one can be given now by this equation here. That's your discharge velocity times the cross sectional area. That's this one here, the cross sectional area. Okay, and this is now your discharge velocity. Okay, now the flow rate, okay, can also be equal to the seepage velocity. Okay, this one here, the seepage velocity, but you don't consider the the total area of the soil specimen, but we only consider the area of the soil solids. No? okay, in the cross section. That's sorry, the areas, rather the area of the voids in the cross section. Now that's your A sub V. Okay. Yeah. Okay. So um here we just flow rate. Okay. So we now have again the discharge velocity times the total area, or that's just equal to the seepage velocity times the area of the voids. Okay, where the total area A is equal to the area of the voids plus the area of the soil solids in the cross section of the specimen. Okay, yeah. Okay. If we now substitute, okay, so if we now substitute this one here in this equation, okay, then we get this one here, wherein the discharge velocity, or rather the flow rate, is now equal to the discharge velocity multiplied by the area of voids plus the area of the soil solids. So that's this one here, but that is just equal to this term here, where that is now equal to the area of the voids times the seepage. No? V sub S is again the seepage velocity. Okay. So again, we are trying to get some relationship between the discharge velocity and the seepage velocity. Okay. Okay, so if we now equate these two now, then I can now cross multiply the area of voids here in such a way that I will now have this equation. Okay, and then if I multiply everything by the length of the specimen, okay, so that means the area of voids times the length will now give me the volume of voids. Okay. And then the area of the soil solids multiplied by the length will give me the volume of solids, soil solids. That's your V sub V and V sub S. Okay. And then the same here, the area of voids multiplied by the length L. So that's the area of voids multiplied by the length L will now give you the volume of voids. Okay. So then we now have if we now look at this equation here, we now have the seepage velocity is now equal to the discharge velocity times this term here. Okay? In such a way that if we divide everything here by the volume of the soil solids, okay, yeah. So this one divided by the volume solids will become 1. We have the volume of voids divided by the volume of solids over the volume of voids divided by the volume of solids. Okay. Now, if we try to recall the volume of voids divided by the volume of solids is now what we call the void ratio. Okay. So that means this one here can be replaced by the void ratio. This term here can also be replaced by the void ratio in such a way that the seepage velocity is now equal to the discharge velocity times 1 plus the void ratio over the void ratio. But again, if we try to recall the definition of porosity, okay, the porosity is equal to the void ratio over 1 plus the void ratio. Okay? So, dire na inverse lang, no? Na reciprocal lang. So then we can just have the discharge velocity over the porosity. No? Nabalik na reverse man so ma 1 over n pod na ang porosity. Okay? So in such a way that the seepage velocity now is equal to the discharge velocity over the porosity n. Okay? So again, the porosity n is defined as the volume of voids over the total volume. Okay? Whereas the void ratio is the volume of voids over the volume of solids. Okay. Now, hydraulic conductivity or coefficient of permeability is generally expressed in units of centimeter per second or meter per second in the SI units. Now, the hydraulic conductivity of soils depends, no, on several factors. You can have the fluid viscosity, okay, the pore size distribution, which can be derived from the grain size distribution. Okay, when I did my PhD work, we had a sort of a numerical approach in such a way that if we have the grain size distribution, then we can also predict the pore size distribution. Okay, yeah. Wherein they will have the same type of curve. Yeah? Okay, for both the grain size and the pore size. Yeah. And then it's also dependent on the void ratio as well as the roughness of the mineral particles. So if the particles are smooth, okay, then you can have an easier flow of water, no? Just like the rocks that you see in rivers. No? Okay, it says that's why you have just those nice rocks, no, na pwede magamit pang lugod, no? Okay, because the roughness there are already being polished by the flow of water, no, to have an easier flow. And then the last factor is the degree of saturation. Okay. Yeah. So again, in this case, for a saturated soil condition, the degree of saturation is 100%. Okay. But in the case of unsaturated soils, um, the hydraulic conductivity here, if we try to recall, this one here, we now try to incorporate another parameter, which is the degree of saturation. No? Okay? For degrees of saturation, say from 1% to 95 or 99%, for example. Yeah? For as long as it's not 100%. Okay? Now, in the case of clay soils, structure plays an important role, okay, in the hydraulic conductivity. Now, other major factors that affect the permeability of clays are the ionic concentration, as well as the thickness of layers of water held to the clay particles, okay, such as the double diffuse layer, okay, which we have discussed, no, in the first meetings. Now, the value of hydraulic conductivity K varies widely for different soils. Okay. Now, some typical values are given here for saturated soils. For example, when we have clean gravels, the hydraulic conductivity can be in the range of 100 centimeters per second to 1 meter per second. Okay. In the case of coarse sand, then you have 1 centimeter per second to 0.01 centimeter per second. Okay, and then for fine sands, that's from 0.01 to 0.001. And then for silty clay, that's from 0.001 to this value here. And then with respect to clay, then you have less than this value here. So we can see here that as the material becomes finer, no? From gravel until clay, the um, the permeability or the coefficient of permeability or the hydraulic conductivity will also become smaller. Okay? So that is the general trend. Okay? So for example, if you don't want rainfall infiltration going into your uh, area, for example, then you can probably cover the area by a clay. We call it a clay barrier. No? Okay, we call it a clay barrier, okay? Because it's um it's barring the water to infiltrate into deep further into the ground. Okay. Also in road constructions for the base course material, normally we prefer such as gravels and sands because they have higher permeabilities. No? So you will have easier drainage, which is quite important in road construction, no? Because if you don't have a good drainage within your road construction, then the road will probably crack later on, no? Because the water will stay behind, no? And it will try to displace the soils as it is being run over by vehicles, no? The road itself. Okay? That's why there are some gradation requirements for the base course, the sub base, and the subgrade material when we do road constructions, for example. Okay. Now, the hydraulic conductivity of unsaturated soils. Okay. The hydraulic conductivity of unsaturated soils is lower. Okay, that is lower as compared to the hydraulic conductivity of saturated soils. Okay, and it increases rapidly with the degree of saturation. Okay, so that's why here in this equation we incorporate here a degree of saturation. Now it's good that I think in the latest version of the principles of geotechnical engineering by DAS. So DAS already slowly incorporated the concept, slowly introducing the concept of unsaturated soils. Okay, if you like, you can read a book on unsaturated soils, which is about 900 pages. Okay, yeah, so which is I read it also during my PhD, where I read that book from cover to cover. Yeah. Now, the hydraulic conductivity of a soil is also related to the properties of the fluid flowing through it by this equation here. No? So that means the permeability is not only a function of the ground, the soil particles in the ground, but also the type of um, um, fluid, no? That is flowing through it. No? For example, water or oil. Okay, yeah. Wherein the such equation K is now equal to the unit weight of water times the K bar, capital K bar, where capital K bar is now referred to as the absolute permeability, expressed in units of L square, such as centimeter square, feet square, and so on. Okay. And then you now have here, this is probably the viscosity of the fluid. Okay. Viscosity fluid. Okay. Now, with respect to the lab, when we do a permeability test, okay, now we can either do the constant head test or we can do the falling head test, okay, approach. Okay, so I'm not sure if you have already done this in the lab, okay, but I think you can do this in the lab. Huh? Okay. Now, in the case of a constant head test, no? A typical arrangement for this one can be shown in this figure here. Okay, so this is, for example, in the lab. I think we have. I think I still remember we have done this in the lab. Okay, this is now the setup for the constant head permeability test. Okay, so with respect to schematics. Okay, so this we now have here, for example, the soil specimen. Okay, I hope you're seeing my cursor. That's the same as the soil specimen here. Okay, and then we have an outlet here. We're in the discharge at the outlet is measured by a graduated flask, such as this one here. It's the same here. Okay, and then we allow a constant flow of water in such a way that this level here, this level and these levels here will be maintained. Okay. So yeah, anyway, you will be doing that in the lab. Huh? Mm, okay. So again, with this is schematics. This the mm, okay. So this H here is now your head. Okay, so this is now your difference in the head. Okay, that's H. Okay, and then this one here is now the length of the soil specimen. Okay, yeah, where water is flowing through. Okay, okay, so kung asa ang direction sa tubig, then that's also where you measure your length L. Okay. So here in this schematic, this is now your soil specimen. And then here we have some porous stone. No? Okay. That confines the soil. Okay. So here, that's this one here. I'm not, I hope it's clear from your end. That's the porous stone. Okay. So in that laboratory setup, the water supply at the inlet is adjusted in such a way that the difference of head, okay? The difference of head, this one here, that's H. That's the difference of head or the head difference between the inlet and the outlet. Okay, this is the inlet and the outlet. Okay? Remains constant during the test period. Okay? Now, after a constant flow rate is established, okay, so in the lab, you will try to adjust the flow here in such a way that, again, you can maintain this head difference okay, between these two water levels. So at a constant flow rate, no, after it is being established, then water is then collected in a graduated flask for a known duration. Okay? Now, with the constant head test, the total volume of water collected may be given by this equation here, wherein Q is now the volume of water collected. A is the area of the cross-section of the soil specimen. That's the cross-sectional area here, this one here, the cross-sectional area for this setup. Okay. And then we multiply it by the discharge velocity, then multiplied by the time, okay, or the duration of water collection. Okay. So this one here is in meters squared, for example. This is meters per second, this velocity, then this is in seconds. So time will cancel out. So what is left is just the volume of water in cubic meters or cubic centimeters, for example. Okay. Okay. But we know that the discharge velocity is equal to K times I, where I is the hydraulic conductivity or the coefficient of permeability, and then I is the hydraulic gradient. Okay? So to recall, the hydraulic gradient I is equal to the head difference over the length L, no? Where the length L is the length of the specimen. Okay. So then we can substitute this one in this equation here in such a way that we now have this equation here for Q. So nawala lang diri ang I, we replace it by the head difference over the length L. Okay. So then just do some algebraic manipulations. Then we can derive the constant head permeability value, K, is now equal to the volume of water collected times the length of the specimen over the area of the specimen times the head difference multiplied by the duration, okay, where you did the experiment. Okay? So this is now the formula for the constant head permeability test. Okay? So in the lab, for example, you just get these parameters and then you can compute for the constant head permeability. Okay. Now, another type of test in the lab is what we call the falling head test. Okay. So a typical arrangement of this test is this one here. Okay. Wherein you have a very long uh, funnel here or a tube here with some gradations. Okay. So in the schematics, that's this one here. That's your standpipe. Okay. And then, yeah, water will flow through the specimen. But in this case, we don't give a constant supply of water, but we allow the water to flow from one level, then going down. Okay, so that means you now have a change in head. Okay, from H sub 1, for example, this one here, I hope you're seeing my cursor, which is now the initial level of water in the standpipe. Okay, and then at a certain time, then it will now just become H sub 2. Okay, this one here is now your um, average head difference. Okay, and then the minute movement of such head is now what you call the DH. Okay, or the differential H. No, if you recall your differential calculus. No, that is our favorite subject. Okay. Okay, so with that setup, okay, so water from a standpipe, okay, flows, okay, through the soil. Okay, then the initial head difference h of one, okay, that is a time zero. Okay, at time zero, you have your h of one is then recorded, and then the water is allowed to flow through the soil specimen such that the final head, as compared to the initial head, um, difference at time t sub 2 is now equal to h sub 2. Okay, so if we go back to the figure again, this is now your initial head difference and between this water level here and this water, okay, where water is flowing out. Okay, this is now your initial head difference, and then this is now your final head difference. Okay, wherein nanadiri ang water level. Okay, yeah, as it goes down. Okay, now so with that, so the rate of flow of water through the specimen, no? At any time t, okay, for the falling head test, okay, can be given by this equation here, no? Wherein Q is now the flow rate, okay, which is now equal to the hydraulic conductivity multiplied by the uh, the head, okay, yeah, the head difference, okay, over the length along the specimen multiplied by the cross-sectional area of the soil specimen. Okay, so this one here, the cross-sectional area of this specimen here. Okay, but that is equal to the negative of A. Okay, where A is the cross-sectional area of the standpipe. Okay, so that's this one here. Okay, the cross-sectional area of the standpipe. Okay, multiplied by the change in head with respect to time. Okay, so that is the change of head with respect to time. That's DHTT. Okay. Okay. So with this equation, okay, then we can now equate these two terms here, this term, and this term here. Okay, so we can probably try to equate the two to get the hydraulic conductivity as far as the falling head test is concerned. Okay? So by just doing some algebraic manipulations, okay, then we will be getting this one here. Okay, yeah. Um, So you now have dt is now equal to the cross-sectional area of the pipe multiplied by the length of the soil specimen over the area of the cross-sectional the cross the, the area cross-section. okay, the soil cross section. Okay, that's your A. And then multiply by the hydraulic conductivity. Okay, and then multiplied everything by the derivative. That's the derivative of H. Okay, with respect to H or the head difference. Okay, so by just integrating these two, okay, then we're with limits of time from 0 to t, and from limits of head difference from h of 1 to h of 2, will now give us this equation here for the time. Okay. Then again, if you manipulate the this one here in such a way that I will now try to solve for k this time, then that will now give me this equation here also in terms of the hydraulic conductivity. Now take note for time, this is the log of E, and then for the K, that is the log of 10. Okay. So again, to recall, this is again the formula for the hydraulic conductivity with respect to the constant head test approach in the lab, whereas this is now the formula for the hydraulic conductivity for the falling head test in the lab. Now, in actual practice, when we measure the permeability, okay, we also do or we do field what we call as field permeability test, okay, within the boreholes after we do the the drilling works, okay. So we then follow the falling head test approach, okay, wherein um, we try to let the water go down with respect to time, and then we measure the time, and then as time goes by, we measure the water levels, okay, wherein we expect it to be decreasing over time. Okay, then we measure it, and then we just apply the Hivors-Lev method, okay, to determine the field permeability. Okay, but the concept there, with respect to that Hibors-Lev approach, the concept there is basically the falling head test approach. Okay, so normally we do permeability tests in the field. No, when we do geotechnical investigations, especially if we are trying to mitigate slopes, for example, wherein we can do some seepage analysis, no? With respect to the slope. Now, now we have here a term which we now call as isotropic. Now, when we say isotropic, that means the hydraulic permeability with respect to the horizontal direction, okay, is roughly the same as the hydraulic conductivity with respect to the vertical direction. Okay, in the case of a two-dimensional flow, because there's what we also call as a three-dimensional flow. Okay, yeah. So three dimensions or three hydraulic conductivities. For the moment, let's just consider two-dimensional groundwater flow with respect to isotropic conditions. Okay. Now, most soils in nature are not isotropic. Okay, they are anisotropic. We call it anisotropic with respect to permeability. Now, for example, in a given soil deposit, the magnitude of K changes with respect to the direction of flow, okay, such as this soil specimen here, wherein the direction of flow may not be strictly horizontal or may not be strictly vertical, but there is an inclined flow, no? Wherein the flow is at is inclined at an alpha from the vertical, no, not from the horizontal. Okay. So the hydraulic conductivity in the vertical, okay, where alpha is zero. Okay. So if alpha is zero, so that means that this arrow here is vertical. And then if alpha is 90 degrees, then that's the horizontal direction. Okay, so that means here the direction, the arrow direction is horizontal, wherein alpha is 90 degrees. So the vertical hydraulic conductivity can then be represented by K sub V. Okay, and then the horizontal hydraulic conductivity can then be represented by K sub H. Okay. So the magnitudes of K sub V and K sub H in a given soil depend on several factors, including the method of deposition in the field. Okay. Now, in literatures, normally we just assume a homogeneous material, but in real, at least in the Philippines, in my experience, for the last few years back, there's really no such thing as uh, a homogeneous soil. No? The soil is heterogeneous by nature. Okay, yeah, or at least a majority of it. Yeah. So that means the hydraulic conductivity in the vertical direction is not necessarily the same in the horizontal direction. Okay. So here, for example, we have some uh, values for the different KH, KV um, ratios, okay, for different soil types as research by these people here. Okay, so here we can see that the horizontal hydraulic conductivity seems to be higher or greater than the vertical hydraulic conductivity, in such a way that in the case of organic silt with peat, okay, then for example, if you use a value of 1.7, so that means the horizontal hydraulic conductivity is about 1.7 times the vertical hydraulic conductivity. Okay. Yeah. For example, here, when you have warped clay in this situation, no? You can just imagine here that's the value there of 40. So that means the horizontal hydraulic conductivity is about 40 times. It's about 40 times higher than the vertical hydraulic conductivity. Okay. Okay. So as I mentioned earlier, in the Philippines, for example, we normally have a stratified soil deposit. No? For example, you have sands, clays, and then sands and clays, and so on and so forth. For example, okay, yeah. We just finished a report, geotechnical report, where we had such kind of stratified soils deposit. No? Somewhere in Laguna, okay, wherein the soil there is yeah basically a combination of sands, uh, clays and the sands and clays and so on, no? Intercalations. Okay. So in that case, in a stratified soil deposit, where the hydraulic conductivity for flow in a given direction changes from layer to layer. Okay. Now, an equivalent hydraulic conductivity, okay, for this situation can be computed to simplify the calculations. Okay. Now, the following derivations, okay, below here. Okay. So the following derivations would relate to the equivalent. Okay, we call it the equivalent hydraulic conductivities for flow in the vertical and the horizontal directions through multi-layered soils with a horizontal stratification. Okay, so a horizontal layering of soils. Okay, okay. So for example, this one here. Okay, we have a stratified soil condition wherein this may probably be sand. Okay, this may probably be clay. This may be silt. Then again, sand, and so on and so forth. Okay, yeah, in such a way that they have their corresponding KH sub 1 and KV sub 1. Okay, for this material here, that's your horizontal hydraulic conductivity for this material in this direction. And then in the vertical direction, you now have the vertical hydraulic conductivity of the soil 1. Okay. Then here, the direction of flow is horizontal. No? Okay. Parallel to the layerings. Okay. So for each soil type, okay, so you now have here your depths, no, for each type of soil in such a way that the total depth is now equal to H. Okay. Okay, so in that again in the figure earlier, we now have n layers of soil with flow in the horizontal direction. Okay. Now, so let us now consider a cross section of unit length. Okay, a unit length, no? Through the uh, n layers. Okay, so if you have here n layers, okay, that's v k sub vn and k sub hn. And then here your h sub n. No, that's the nth layer. Okay, and then perpendicular to the direction of flow. Okay, wherein the total flow through the cross section in unit time can be written by this one here for the wherein the total flow is now equal to the average discharge velocity, okay, multiplied by 1 because we are considering a unit length, okay, a unit length. When you say unit, that's 1, okay, multiplied by H, okay. That is for a single soil um, layer. Okay, but for multiple layers, okay, so then the average discharge velocity V, okay, is now being divided into discharge velocities of flow in the different layers denoted by this subscript. No? For example, this is the first layer, the second layer, the third, and the fourth, and so on and so forth, until you reach the nth layer. Okay. Okay. Now, if KH sub 1 and so on and so forth until KH sub n, okay, are defined as the hydraulic conductivities of the individual layers in the horizontal direction. Okay, so that's this one here. Okay. And then K sub capital H EQ, or that's equivalent, no? Equivalent. Okay, is now defined as the equivalent hydraulic conductivity in the horizontal direction. Then, as per Darcy's law, okay, wherein the discharge velocity is equal now to the equivalent um, um, horizontal hydraulic conductivity is now multiplied by the equivalent hydraulic gradient. Okay, that's your I. Okay. But if we have multiple layers, then okay, this equivalent is equal to the discharge velocities corresponding to each layer until the nth layer. Okay? And then for the hydraulic gradient, the equivalent I, okay, the equivalent I is also equal to it's just equal to the hydraulic gradients for all the layers. Okay. So if the equivalent hydraulic gradient is just equal to the hydraulic gradients for each layer. Okay. So then we um, we can now have this equation here. Okay. Wherein the equivalent horizontal hydraulic conductivity is just equal to 1 over the total depth of the soil layers, okay, multiplied by the yeah, kh sub 1 times h sub 1, wherein that is now kh sub 1 times h sub 1, okay, plus this one at layer 2, then plus this one at layer 3, until you reach the end layer. Okay? That's the equivalent hydraulic conductivity. Okay. Okay. Now, this time, we now have, again, say the same soil layering. Okay. For example, here you have about 4 or 5 layers, okay, until the nth layer. Okay. But this time, the direction of flow is not parallel to the layering of the soils, but rather this time, the direction of flow is now vertical, which is now perpendicular to the soil layering. Okay. Yeah. So in this case, we now have your head differences, okay, in such a way that if I put a piezometer here, then this is now the height of my, or this is now my piezometric level. Then if I put a piezometer here, this is now my piezometric level, and so on and so forth. Okay. And then you notice that here at this level, it has a higher piezometric level as compared to this one here at this point, because the direction of flow is coming from this direction going here or going up. Okay. Okay. So just to repeat, that figure there shows, or this figure here shows the n layers of soil with flow in the vertical direction. Okay. Um, in that case, the velocity of flow through all the layers can just be considered the same. Okay. However, the total head loss H, okay, here, the total head loss H, okay, is equal to the sum of the head losses in all the layers. Okay, so that's this one here. Okay, that's equation 7.42 in your book. Okay, wherein uh, the the total head loss is just equal to the sum of these individual head losses. Okay. So considering that the velocity of flow is the same in all layers, then the discharge velocity is just equal to the discharge velocity on each particular layer until the nth layer. Okay, so they're just equal. Okay. So if we now again apply Darcy's law in this equation here, okay, then we have the equivalent. Okay, we now have the equivalent vertical hydraulic conductivity, okay, multiplied by the hydraulic gradient. So that's h, small h over h. Let's see. Okay, that's your h. Okay, that's the head loss over or divided by the length of flow. No? That's the length of flow. In this case, that's your h. No? That's your length of flow. So this head loss over the length of flow, h, because it's in the vertical direction, and that is now your hydraulic gradient. Okay? So then that is just equal to this Ki at the first soil layer, and then the second, and then the third, and so on and so forth until you reach the end layer. Okay. Okay. So uh, from this equation here, okay, from this equation, we can replace, okay, we can replace h sub 1 by capital H sub 1 multiplied by the hydraulic gradient at 1. Okay, because again, we recall the hydraulic gradient is equal to the head loss over the length of flow. Okay, then we can then just replace all terms here by each of these terms. No? Okay, so then if we now substitute equation 7.43 to equation 7.44 here in your book. Okay. Again, if you have the book, you can always refer to your book. Okay. If you cannot see my slides clearly. Okay. Then this combination of these two equations here will now give us the formula for the equivalent vertical hydraulic conductivity. Okay, which is now given by this equation. Okay? So again, you have your H and then H sub 1 until H sub n. That's this one here. No? Okay, that's your, sorry, this is now your H. Okay, and then this is now your H sub 1 until H sub capital H sub n. Okay, okay, that's your capital H. Then these are now the individual vertical hydraulic conductivities. Okay. Now, so far we have been discussing about water flows, okay, for stratified soil deposits, no? Either in the horizontal direction as well as in the vertical direction. Okay. Now, in the field, we can also have the average hydraulic conductivity of a soil deposit uh, in the direction of a flow um, can be determined by performing a pumping test, okay, from wells. Okay, if you have a well, for example, a water well, we can do pumping tests there. I think that the WRC, for example, or the Water Resources Center, they do a lot of pumping tests. Okay, um, to check no, the hydraulic conductivity in water wells, no, for example. Okay, so with that, we have here a figure. Okay, this one here. Okay, so let me just go through this text. So that figure shows a case where the top permeable layer, whose hydraulic conductivity has to be determined. Okay, but that um, condition is unconfined. Okay, it is an unconfined condition. Okay, and then it is underlain by an impermeable layer. Okay, so in this case, we sometimes call it an unconfined aquifer. Okay, we call it an unconfined aquifer. So um, during such test, this during this pumping test, no? Okay, so the water is pumped out at a constant rate from a test well that has a perforated casing. Okay, and then several observation wells are at various radial distances are made around the test well. Okay. Now, continuous observations of the water level in the test well and in the observation wells are made after the start of pumping until a steady state is reached. Just like when we do the constant head test in the lab. Okay. Now, the steady state condition in that water well is established when the water level in the test well okay, as well as the observation wells becomes constant. Okay. So if you go back to this figure here, again, this is now your impermeable layer. Okay. And this is now your unconfined permeable layer, which we also call an unconfined aquifer. Okay. In the subject on hydrogeology or geohydrology. Okay. Which was my master's degree as well. This is then, or your unconfined aquifer is then underlain by an impermeable stratum. Okay. Yeah. So this one here can be your unconfined aquifer. In hydrogeological terms, we can also call this the aquifuge or the aquiclude, for example. Okay. And so again, as mentioned earlier, we pump out water. This is now your test well or your water well, for example, this one here. And then these are now your observation wells. No? Okay. Um, this can probably be drilled by or by bore. This is what we call the boreholes. Okay. And this is now your pump well. No? Okay. Where you obstruct water, no, for groundwater supply, for example. Okay. So then we now have here the distances, R1 and R sub 2, the radial distances from the observation well to to the center of the test well. Okay. So initially, we now have here the water table. Okay. So in the case of an unconfined aquifer, we sometimes call it the water table. This is now the water table here. Okay. Then this is now the water table before you started pumping. And then after you started pumping, then this is now the blue line here is now what we call the drawdown curve. Okay, the drawdown curve. Okay, wherein at any point on the drawdown curve, you can have your head difference. No? You can have your head difference. For example, this one here is your H sub 1 corresponding to this observation well. And then this is also your corresponding H sub 2, okay, or your head difference corresponding to this observation well. Okay. So it is important to understand this, especially if you want to um, uh, do dewatering works. No? When you do dewatering works, um, in excavations, in construction excavations, for example, where the groundwater level is quite high, so then we need to uh, to have a drawdown. No? Okay, so we try to lower the groundwater level in such a way that if this is now my initial water level, and then I need to excavate, let's say, until this depth. Okay, above below the groundwater level. Okay, listen this one here. So what we do in actual construction is we do some pits and then we put pumps, okay, and then the groundwater level from this initial level will now decrease. Okay, and then you can have here a dry working platform. Okay, wherein you can start working with your foundations. Okay, so then this is now what you call your drawdown curve. Okay. Okay. So with that, the expression, no, for the rate of flow of the groundwater, okay, the groundwater or the groundwater flow rather into the well, okay, um, which is also equal to the rate of discharge from pumping, okay, because whatever you pump out, okay, if you pump out a constant water flow, okay, above, then that is probably presumed as this same as the rate of inflow of groundwater into the well. Okay. So then with that, the flow rate can be given by this equation here, where this is now the hydraulic permeability. Okay. And then, yeah, this is now uh, 2 pi r, that's basically the circumference. okay, multiplied by the H. Okay, so that's basically um, this one here. Okay, that's 2 pi r. Okay, multiplied by this H here. Okay, yeah. And then, okay, that's actually um, the uh, the volume. Okay, that's the volume. Okay, then multiplied by the change in the head with respect to the radius. Okay, that's the change in head with respect to the radius or the radial distance. Okay, okay. So from here, we can just do some algebraic manipulation. Okay, so we break the differential r with respect to the differential h. Okay, and then we put r here, then we put h here. Okay, then we take out the constants. Okay, now take note here, the flow rate is constant because you're abstracting a constant flow of water, so that cannot be included within the integral sign. Okay, so we are now doing some integral calculus. Okay, and then your limits of your integral is R1 and R2 as well as H sub 1 and H sub 2. No? Those are your limits of integration. Okay. So here, this is now your H sub 1 and H sub 2 because H sub 2 will only occur as we are having a drawdown. Okay. Okay, so just doing some integral calculus, okay, calculations, then we can derive the formula for the hydraulic conductivity for the flow of groundwater into pumping wells, for example, no, for water supply purposes, for example. Okay. Yeah. But this formula is only applicable if you have an unconfined aquifer, no? Wherein you have here an unconfined permeable layer underlain by an impermeable stratum. No? So when you say permeable, that means water can flow through it. Impermeable, yeah, water cannot flow through it. Okay. Now, so that's the case for unconfined aquifer. Now, we also have the average hydraulic conductivity for the case of a confined, this time. You have a confined aquifer, but again, by doing pumping tests from a well with a perforated casing, okay, that means that you have here there basically a PVC pipe, for example, where you put holes, okay, along the casing. Now, that's what we mean by perforated. Okay. And then that penetrates the full depth of the aquifer. Okay. And by observing the piezometric level, okay, in a number of observation wells at various radial distances. No? So, okay, so let's see the figure for that. Okay, so this one here. So basically, we just have the same figure as the unconfined aquifer. The only difference here, no, wherein you still have your test well here, and then this is now your observation wells. Okay, so here we penetrate the full depth of the confined aquifer. This one here. Now, this is now your confined aquifer. Um, and then this is overlain and underlain by impermeable layers. Okay. Now, normally this one here can be sands or gravels. Okay, your for your confined aquifer, and then for the impermeable layer, maybe some clays and some rocks, for example. Okay, so that means the confined aquifer here is acting like a pipe. No? Okay, it's acting like a pipe wherein water cannot go out from the pipe. Okay, so if you're seeing my cursor, water cannot go here up and it cannot go down. It can just flow in the horizontal direction because the permeability here in the confined aquifer is, for example, higher in the horizontal direction than these layers here. Okay, so then water will flow through here, go up. If you're doing a pumping test, then water will flow through here, going up, no, in a radial direction. Yeah. So then, considering a confined aquifer where pumping is continued at a uniform rate Q, okay, until a steady state is reached. No? Okay, you have a constant head, no? For example, a constant head test in the lab. Okay, so here, okay, we we use the same formula, okay? But take note, here you have small h, okay? That's, sorry, that's this one here, small h, okay? But here, in the confined aquifer, you have this h here, no? Okay? Not this h, no? But you have this h here because it is a confined aquifer medium. Okay? So you consider this h, okay? So that's the this one here. So that's the difference. No? That's the difference. Okay. And then um, so we just try to do some algebraic manipulations. Okay. And then we have here again your uh, dr over r. Okay. That's the radial distances. Okay. That's this one here. Okay. That's your radial distance. Okay. Then here we just have the R1 and R2 for the two observation wells. Okay. So by just doing integration, wherein the limits are R1 and R2, as well as H1 and H sub 2 for this one here, for these two observation wells. And these are now your limits of integration. So again, just doing some integral calculus, then you will get this formula here for the hydraulic conductivity. Take note, that is in a confined aquifer medium. Okay, yeah, a confined aquifer, which is quite different from the unconfined aquifer. Okay? So that means for you to apply these equations here, it's really very important to do some geotechnical investigations, and then you try to identify or distinguish the layers, no? The layerings in your ground condition, whether you're having an unconfined aquifer or if you're having a confined aquifer. Okay, and normally that can also be identified by hydrogeologists, okay, such as myself. Okay? So basically, I have two fields. No? I have hydrogeology as well as um, unsaturated soil mechanics, no? In geotechnical engineering. So we normally focus on these topics in hydrogeology or geohydrology. Okay. Um, okay. So far, we have considered simple cases for which direct application of Darcy's law, okay, was required to calculate the flow of water through the soil. Okay. Now, in many instances, the flow of water through soil is not in one direction only. Okay, such as a horizontal and vertical direction, nor is it uniform over the entire area perpendicular to the flow. As Okay. So, in such cases, the groundwater flow is generally calculated by the use of graphs, which we now refer to as flow nets. We call them flow nets. Okay. Now, the concept of the flow net is actually based on the Laplace equation of continuity. No? If you still remember your subject in differential equations, we have the Laplace transforms, okay, equations, okay. So here it's just the same. That's the Laplace equation of continuity, which governs the steady flow condition for a given point in the soil mass, okay. So let us now try to arrive at this Laplace equation of continuity. Okay. Yeah. So to derive the Laplace differential equation of continuity, we can probably consider, no? Let me just go to this text. We can probably consider a single row of sheet piles that have been driven into a permeable soil layer, such as the one shown here. Okay, we try to drive a sheet pile. In actual construction, we normally use sheet piles. Okay, if you want to if you want to cut off, no, if you try to cut off the water flow, for example, no, in excavation, for example, if you can drive the sheet pile, okay, so such as this one here, okay, okay, so in this figure, you now have H sub 1, which is the head at this point, and then this is now your H sub 2, which is the head at this water level, in such a way that yeah um, okay, wherein uh, here we can consider a soil element, okay, with a certain um, head difference, no? Okay, so in that figure, the row of sheet piles is assumed, no, to be impervious, okay, and then the steady state flow of water from the upstream side to the downstream side through the permeable layer is considered to be two-dimensional flow. Okay, so this one here. No? So this is considered to be two-dimensional flow. It's not horizontal flow. It is not vertical flow, but the flow is two-dimensional, something like that, for example. No? Okay. Now, for flow at a point A, so this one here, okay, for flow at a point A, we consider an elemental soil block, okay, wherein the block has dimensions um, dx, dy, and dz. No? So that's dx, dz, and then dy is perpendicular to the screen, no? Perpendicular to the screen. Okay. So in an enlarged figure for the soil element, okay. So so we now have here the dimensions dx, dz, and dy. Okay, and then yeah, we now have here the inflow. Okay, which is now this term here. Okay, and then this is now the outflow. Okay, in the horizontal direction. Okay, and then this is now the inflow term and the outflow term in the vertical direction, which means that for this soil element block, um, two-dimensional flow is happening. No, flow is happening in the horizontal direction as well as in the vertical direction. So in this case, the flow is probably already going in this direction, something like that. No? Wherein you have a vertical flow and a horizontal flow. Okay. Okay. Now, assuming that water is incompressible and that no volume change in the soil mass occurs, okay? Then we know that the total rate of inflow is equal to the total rate of outflow. Now, we learned this in fluid mechanics. So this is now the total inflow, and this is now the total outflow. Okay, in such a way that if we now subtract this one here, then what is left is just this equation here. Okay. Now, with Darcy's law, okay, then we can now replace these velocities here by the hydraulic conductivities as well as the hydraulic gradients. Okay, wherein the hydraulic gradient can be represented by um, the the partial change of the head with respect to x as well as the partial change of the head with respect to z. That is now your x and z. Okay. So with that, if we now substitute this term and this term here in equation 8.1, so that will now give us this equation 8.4. Okay. Um, yes. So take note. This is now the uh, the first partial derivative. If we substitute this one here, then we now have the second partial derivative with respect to x and with respect to z. Now, this equation is considering that we have an anisotropic condition, okay, wherein Kx and Kz are different. But if we have an isotropic condition, that is Kx and Kz are equal, then they are just the same. So that means these two are just the same. So we can divide everything by the same term. So that means, yeah, it is now, this equation 8.4 is now simplified to equation 8.5, such as this one here. Okay. So this is now the Laplace equation for, um, okay, the Laplace equation of continuity. Okay. So interpreting this equation now with respect to flow nets, then the continuity equation, okay, in such isotropic medium, okay, take note, this is isotropic condition, okay, represents, okay, now it now represents two orthogonal families of curves, if you still recall your differential equations, okay? Now, there we have, or we call it orthogonal families of curves, but here in geotechnical engineering, these two orthogonal families of curves are now what we call as the flow lines and the equipotential lines, okay? Now, a flow line is a line along which a water particle will travel from the upstream to the downstream side in the permeable soil medium, whereas an equipotential line is a line along which the potential head at all points is equal. Thus, if piezometers are placed at different points along an equipotential line, then the water level will rise to the same elevation in all of those piezometers. Okay. So if we look at this figure here, for example, okay. Yeah. So here we now have what this is now what we call, because we know that the flow of water is two-dimensional, flowing from this direction going to this direction. Okay, so water flow because this is a higher water level, so naturally water will seep through here and then it will try to flow here because the sheet pile is impermeable. So that means this one here is an example of a flow line, and then perpendicular to the flow line, this is now your equipotential line, in such a way that if I put piezometers in each of the points in this equipotential line, then I will have the same piezometric levels. Okay, so this is now what we call the orthogonal families of curves that you learned in differential equations. No? Orthogonal, that means they are perpendicular to each other. Okay. Okay. Now, a combination of a number of flow lines, okay, if you're seeing my cursor, a combination of a number of flow lines and equipotential lines is now what we call a flow net. Okay. Now, flow nets, again, are constructed for the calculation of groundwater flow and the evaluation of heads in the media, okay, or your soil media. Okay. Now, to complete the graphic construction of a flow net, now one must draw the flow and the equipotential lines in such a way that the equipotential lines intersect the flow lines at right angles, not just like this one here. No? The equipotential line intersect the flow line at right angles, this one here. Okay? And then the flow elements formed are approximate squares. Okay, approximately squares. Okay, not exactly squares, but approximately squares. Okay. Here, this figure here is now an example of a completed flow net. No? Wherein in this completed flow net, yeah, these are now the flow lines. Okay, and then these are now the this is now the equipotential lines. Okay. Now, in this figure here, okay, so in that figure, no, for an isotropic permeable layer, we have NF there. Okay, we have the term NF, which is the number of flow channels in the flow net. And then ND is the number of potential drops. Okay, yeah, potential drop. Okay. So for example, here in this figure, the number of flow channels is 4. Okay, let's see. You have 1. This is 1 flow channel, 2, 3, and 4. Okay, this one here. You have 4 flow channels, for example. Okay. Now, in 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 doing such exercise, now drawing a flow net takes several trials. No? Okay, it takes several trials because you need to have you need to have approximate squares. Okay, yeah. So while constructing the flow net, we need to keep the boundary conditions in mind. Okay, so for example, here in this figure, we have to take note of the 4 boundary conditions that would apply. So for example, the first condition is that the upstream and the downstream surfaces of the permeable layer, that's this one here, the upstream and the downstream um, um, surface layers, this one here, we treat them as equipotential lines, no? In such a way that the flow lines will be perpendicular to this equipotential line. Okay. Okay. So that's the second condition. Okay. So the flow lines intersect the equipotential lines at right angles. Okay. So this one here. Okay. The flow lines intersects the equipotential lines at right angles. Okay. At right angles. Okay, now also the boundary of the impervious layer, that's this one here. Sorry, that's this one here. Okay, this boundary can also be treated as a flow line. Okay, so this is a flow line, a flow line, and then a flow line. Then this is also a flow line. In such a way that the equipotential lines, this one and this one, are perpendicular to, again, to the flow line. Okay, so when we draw the flow net, okay, okay, okay. Now, in any flow net, the strip between any two adjacent flow lines is now what we call a flow channel. Okay, so for example, this figure here, we have now what we call a flow channel. Now, this is now one flow channel between two flow lines. Okay, this is now a flow line and a flow line, and we now have here four equipotential lines, for example, wherein we have drawn approximate squares. No, okay, this is one approximate square, another approximate square, and then another approximate square. Okay, okay. So so in this figure in this flow channel, so we now call H of 1, H of 2, H of 3, and H of 4 as the piezometric levels corresponding to the equipotential lines. No? So in this case, at any point in this equipotential line, then you only have the same H head. You have the same head. No? Okay, so they will have the same piezometric level. Okay? So in that case, the rate of seepage through the flow channel per unit length perpendicular to the vertical section, okay, through the permeable layer is given here in this equation, okay, um, presuming that there is no flow across the flow lines. No? That means flow is just going through here. No? Flow cannot go through these two flow lines. No? It's just going uh, sort of parallel, no? Parallel to the flow line, no? Because these are your flow lines. Okay. So for each square element, you have your corresponding flow rates, no? Okay, delta Q1, delta Q2, and delta Q3, in such a way that these flow rates are just equal, okay, considering Darcy's um, um, law as well, and that's it's just equal to the change in the flow rate, okay? Then with Darcy's law, okay, we can replace the flow rate with this formula KIA, where the hydraulic gradient I is now given by this one here, by the head loss with respect to length L. Okay, that's your head loss here with respect to this length L. Okay, okay, okay. And then, sorry, okay, and and then we also have, okay, after we have the flow elements, no, which we draw as approximate squares, okay, then we have also the drop, no, in the piezometric level between any two adjacent equipotential lines, which are also considered as the same, okay, so that which we now call as the potential drop. No? So that means the potential drop from H of 1 to H of 2 is just equal to the potential drop from H of 2 to H of 3, as well as the potential drop from H of 3 to H sub 4. Okay, in such a way that we have this one here, which is just equal to this head difference, okay, this head difference between the upstream and the downstream side, okay, that's this one here. The head difference between the upstream and the downstream side. Where is that? Okay, yeah. Okay, so yeah, so that's this one here. That's your H here. The head difference between A sub 1 and A sub 2, for example. Okay. Okay, and then yeah, if we now replace this one, okay, in this equation here, okay, in this equation, then we now have your delta Q is now equal to K multiplied by this term here. Okay, where ND is the number of potential drops. Okay. So if we go back to the figure here, okay, so in this case, we now have six potential drops. No? So you have one, two, three, four, five, and six potential drops. That's why your ND here is six. And then you have four flow channels. No? One, two, three, and four. Okay. Okay. So if the number of flow channels, okay, in a flow net, now because this one is only good for one flow channel. Okay, so it's only good for one flow channel. So to get now the total flow rate of flow through all the channels per unit length can now be given by this equation here, wherein we just multiply this formula for one flow channel by the number of flow channels. No? Okay, so for example, in this figure here, we multiply it by 4 no? Because here, the number of flow channels is equal to 4. Okay, so that is how we derive the um, the flow rate using a flow net, no? Considering a flow net approach. No? If you try to draw it yourself. No? But again, in practice, that's a bit tedious to do. So in practice, what we normally do is we just use a software. Okay, and then for example, this one here, this is actually your sheet pile. Actually, this is just the same example. This one here, we put sheet pile, but we just represent it in we just model it. Okay, and this case, this is now a seepage model for an excavation, for example, wherein you have water on top. Then this is now the ground surface covered by water. Then, for example, you need to do some excavation here, where this is now your excavation depth. But in order for water not going into the excavations, we try to put some sheet piles. We represent the sheet piles in the model as an impermeable layer. Okay. And then with that, then you now have this flow net here. And this is now what you call your flow net. Where this is now your flow lines. Okay, your flow lines. And these are now your equipotential lines. Okay, intersecting the flow lines. Okay. So here we can see with the flow net that the direction of flow is from this direction going into this direction. So that means water will go out here. Okay. So that's why in construction, what we do after we have the sheet piles, we still make here some pits. No? Okay. We put here some pits. Okay. And then we put pumps, then try to extract it and then throw it here outside so that this level will become dry. Then you can start constructing your foundations here. Okay. Now, the reason we put the some pits on the sides because of this one here, wherein in the seepage analysis in modeling, okay, um, we can see here the velocity vectors. No, we now call this the velocity vectors. Okay, wherein we can see the direction of the flow of water, which is quite high. No, the flow of water is quite high in this part here. No, okay, flow. Wherein this is now the discharge amount or the discharge value at this level, which is yeah, it's quite it's just the sum of the discharges from this point and this point. No? So mag-abot sila dire. Okay, then this is going to be the total discharge. Okay. Now, this discharge rate here, if you know this one, then this can be the basis of your pumps. Okay. When you buy a pump that has a pump capacity or pumping capacity higher than the discharge, the water discharge coming out from the ground. Okay. In order for you to make this embedment depth here dry no? During working. So in actual construction, we make sure that the pumps that we buy should not break down. No? Okay, because you can just imagine if there are people working here, okay, and then you have water going out all the time. So if the pumps will break down, then okay, you can just imagine this will become a swimming pool. Okay, and that will cover the all the people the workers as well. So we always prepare um, spare pumps. No? There are always spare pumps because if the pumps will break down, we immediately put the other pumps. Okay. Okay, so I guess that's the end of my discussion. So let's have some examples here. Okay, so we have about 15 minutes left, I think. Yeah. So here we are asked to find the flow rate in cubic meters per second per meter length at right angles to the cross section as shown here. Okay, that's a per meter length. Okay, per meter length perpendicular, no? Okay, perpendicular to the screen, for example. Okay. So we are asked to find the flow rate in this permeable layer, which is a bit confined. Okay, we have a confined layer because you have here a permeable layer, and then this one is an impermeable layer. Okay, so this is now the direction of flow. Okay. So again, if we now try to put piezometers, okay, put piezometers here, then we now have here the piezometric levels. Okay, so normally with the direction of flow, the piezometric level at the upstream side, this is now your upstream side and your downstream side, the piezometric level is always higher than the downstream side. Okay, that will determine the direction of flow. Okay, so in this case, we would know the direction of flow is going from this point to this point. Okay? Where in such a way you have now your head loss H. Okay, then H of 1 is now the thickness of the permeable layer. Okay, so to determine now the flow rate, first we need to get the hydraulic gradient I, wherein the hydraulic gradient is equal to H, the head loss H, over this length. No? Okay, this inclined length. But what is given is a horizontal length. Okay, but we know the inclination of this flow direction with respect to this one here, with respect to the horizontal, which is now alpha. So if we want to determine this length, okay, so that is equivalent to S over cosine alpha. No? You're actually determining here the hypotenuse. Okay? Yeah. So that's this one. No? That's this length. You derive the hypotenuse with respect to S, no? Wherein this is now your alpha. No? Alpha. Okay. So then we have now the hydraulic gradient. Okay. Um, okay, so this is now your hydraulic gradient. Okay. This one here. So to determine the flow rate, then we now just have the formula KIA, where K is now the hydraulic conductivity. I think that's given, this one here. Okay. And then small h is 4 meters. Okay, this one here. Then alpha is 8 degrees. Okay, and then S is, okay, this S is 50 meters. That's given. Okay. Then we need the area. No? We need the area of this permeable layer, wherein for the area you have this. Yeah, you have this one here. No? Um, Sorry, you have. If this is the flow, then this is not the area that we consider, but rather this one here. No? The hypotenuse, no? The hypotenuse, just like a pipe. No? This is the hypotenuse multiplied by 1, no? 1 perpendicular to the screen. Okay, that's your area. Okay, perpendicular to the screen. So for this one, we need to get the hypotenuse, no? Because we have H1 then we now have this. If we get the hypotenuse, it's just the same as alpha. Okay, alpha. So to get the sorry, uh, no, rather this is now H1 rather will now act as your hypotenuse. Then you need to get this side rather. Huh? Okay. So if you need to get this side, then this acts as the hypotenuse. You now have alpha here. So this side will now become H sub 1 cosine of alpha. Okay. And then just substitute H sub 1, which is 3. Then you get now the flow rate. Okay. Which is now in cubic meters per second per meter length. Okay. Per meter length of soil. Okay. That's this one here. Per meter length of soil. No? Per meter length of soil. Okay. Okay, so another example, here we are asked to get, um, okay, we are asked to get the ratio, or we are asked to estimate rather, the ratio of the equivalent hydraulic conductivity. No? So when you say the ratio of the equivalent hydraulic conductivity, that's the ratio of the equivalent horizontal hydraulic conductivity as well as the equivalent vertical hydraulic conductivity. Okay. Then we are given these uh, values here. Okay. Now, in this case, we are uh, having an isotropic material because we are only given KH1, KH2, and KH3. That means the vertical and the horizontal hydraulic conductivities are just the same. Okay. So just like this figure here. Okay. So we're actually having a problem, something like this. No? Okay, wherein we are given the H values, and then we are also given the K values. Now in that problem, KH and KV is just the same. So we are having an isotropic medium. Okay. Okay. So with that, for the equivalent hydraulic conductivity, we just follow this formula as given earlier. And then we just substitute these values here. Okay. Then we get now the equivalent hydraulic conductivity. Now, for the vertical hydraulic conductivity, okay, again, you're given these parameters here, okay, then we just simply substitute the given values, wherein K sub V is just equal to your K, because K sub V and K sub H is just equal in this case, having an isotropic medium, okay, for example. So just substitute the values here, and then so we get the value for the equivalent vertical hydraulic conductivity. So thus to get the ratio now, then we just simply substitute this value here, and then this value here, then this is now the ratio of the equivalent hydraulic conductivity. Okay. So I guess this is at the end of my slide. So I think we have a few minutes left. So if you have some questions or clarifications, it seems that yeah, my time is always just right. I don't have time to make to have a break. Okay? Apologies for that. No? Okay. If you have some questions or clarifications, let me just stop share. So again, in actual practice, we already use softwares. No? Okay, we use softwares to do seepage analysis. Okay. Yes, there seems to be a question here. Um, is a soil with a high level of seepage a good thing or a bad thing? Okay. Yeah, this is a very good question. Okay. So depending on your goal, okay. For example, in case of construction, okay, in the case of construction, wherein um, we wherein you have the groundwater level above, okay, above the excavation depth, okay. Then in that case, a soil with a high seepage level, no? Or with a high hydraulic conductivity or high permeability, it may be a bad thing, no? Because we need to buy large pumps, okay, just to remove water, okay, in order for us to have a dry platform. So in that case, it may not be a good thing. But if we are talking of hydrogeology, okay, or geohydrology, wherein the goal is for water supply purposes, okay, supply of water for drinking purposes, then a soil with a high seepage or high hydraulic conductivity, we actually call them aquifers, okay? So soils with high seepage or high hydraulic conductivity, we call them aquifers. Normally in groundwater supply, for water supply companies like the Metro Cebu Water District or the Manila Water, they normally look for aquifers, okay? Because these are the soils wherein you have high seepage and they want higher permeability so that we can abstract um, um, groundwater with high amounts to be supplied for whatever purpose we need for it. No? Okay, for drinking water or whatever other purpose. Okay, so it depends on the goal. Okay, it depends on the goal. Okay. Later this morning, we just had a discussion with one client. No? That basically, this was also his question. Um, that was the same site in Laguna. Okay, because the groundwater level there, we drilled about 6 boreholes. Then the groundwater level is around 1 to 2 meters. No? And then the embedment depths for the foundations, that's about 3 buildings. There's a warehouse type buildings. The embedment depths are around 2.5 meters. Okay, but the groundwater levels are around 1 to 1.5. Okay, yeah. So on one side, they were asking about dewatering issues. Okay, so we gave them some advice. Okay, so in this case, when you excavate the foundation, so you need to do some dewatering. You might need to put some sumps. But at the same time, you have a high groundwater level. So the client was asking, okay, can we probably use this for water supply purposes? Okay. So then I answered them now, yeah, you can do that because you have a high groundwater table. But yeah, considering the material on that particular site, I don't recommend because it has a very low permeability. Because so they may not have a good yield. Okay, for that. But again, it depends on the purpose. And then I just advise them that if you really want, you can do a pumping test or yeah, you can do permeability tests if you like. But based on just literature, based on what I saw from the geotechnical report, um, it's not recommended for water supply. Okay? But it's good for dewatering purposes no? When they construct the foundations because I can foresee there that the permeability values are quite low. Okay, um, so there might be just small flow into the excavations. So they just need maybe some minor pumps for that no? To excavate during construction. Okay, very good question. Okay, any other questions so far? How can we validate? There's a question here. How can we validate our results with regards to seepage analysis? Uh, f- yeah, again, that's a very good question. Normally, it's a bit difficult to validate that, unless you you really confine the material. Okay, you confine the material. Now we had one project in Batangas, for example, wherein I don't know if I mentioned this to you before, wherein there was a highway in Batangas where we were building a power plant, and then that highway uh, collapsed. Okay, because we were inserting pipes, no, from the sea going to the power plant for cooling water purposes. Okay, and so that collapsed. Okay, but we were not the ones who initially constructed. We just followed the construction. But later on, we found out that there was something wrong with the construction. And so we tried to validate. We tried to validate that the reason for that collapse is because of the strong seepage from the sea side, from the seaside going to the excavation. Okay, wherein we tried to protect the excavation. Okay, so we tried to validate that with a seepage analysis. But as to validating the actual results in the actual field, I think it's a bit challenging. Huh? It's a bit challenging. It's not that easy. Yeah. Because you can have flow everywhere. Okay, you can have flow everywhere. So the best you can do is just try to assess what you get in the seepage analysis, then try to validate in the field. For example, you put pumps higher than those. You put pumps higher than those what you saw in the seepage analysis, and then if what you expect in the field is working, for example, when I put these pumps with pumping rates higher than the discharge rate that I saw in the seepage analysis, then maybe my calculation is correct, something like that. But as to validate the actual value, it might be a bit difficult. Again, a very good question. Any other questions so far? Okay. Sir, are there ways to artificially increase or decrease seepage? Okay, if you talk of groundwater flow, um, let's see. With respect to groundwater flow, um, because when you talk of groundwater flow, the seepage there is just actually dependent on the rainfall infiltration, for example. Okay. Um, if the if the head differences, no? If the head differences will become high, okay, if the head differences will become high, they will have an increased seepage. Okay, that's the effect. That's why we discuss head differences, because the higher the head differences, the faster is the seepage. Okay, but for you to do that artificially, yeah, maybe you can inject. You can do injection wells. Okay, probably. That can probably increase the seepage. Okay. Um, but to decrease the seepage, yeah, you can probably do cut off walls, no? Like a sheet pass. Okay. But but normally we don't. Normally in construction, for example, we had one project in Sorsogon before, wherein the that project we are building a geothermal power plant. The groundwater level is quite high, also around 1 to 1.5 meters. But when we were building the switchyard area, okay, we noticed that the switchyard area, it was full of dump. Okay, it was a backfill area. It was a dump area. So we have to excavate everything there so that we can, and then we need to rebuild. No, we need to rebuild. Uh, the platform so that we can build those gantry towers for the switchyard, okay, for us to be able to distribute the power, okay, to the power grid. Now, there we had a chance to try to discharge, okay, the groundwater. Where in there we installed what they call as horizontal drains, okay, horizontal drains, okay, wherein we try to let the water just we just let the water flow, okay. But the goal there was not to increase or decrease seepage, okay. The goal there was just to try to maintain the flow, no? To minimize the increase in the pore water pressure. Okay, yeah, because if you um, um, if you have an increased pore water pressure, that's not good if you have slopes, no? If you have slope, because the slopes can fail, okay? Because there was a slope in that project. Okay. Yeah. I just recalled, no, when I was still doing my master's degree in Holland, in Amsterdam, I think it's no, there was one part in Holland. I'm not. I think it's not Amsterdam, but there was one part there wherein what they did is uh, they they want to improve their groundwater supply. They want to improve their groundwater supply for that area. So what they did is because they have a lot of rivers in Holland. So what they do is they abstract water from the river and then they inject it back into the ground, no? By using injection wells. Okay. And then they allow it to flow into the ground. And then somewhere else they try to obstruct it. Then they get cleaner water. Because when water passes through the ground, it usually is becomes cleaner. Okay. That's why if you can obstruct groundwater, it's always there will be less cost in treating it as compared to surface water. Okay. But again, sometimes there are environmental issues with that. No? Okay. So I guess that's one way of um, artificially treating with seepage. Okay. But as to increase or decrease seepage, I'm not really sure. Okay. Normally, for example, WRC there in Cebu, they just do pump test, no? A pumping test, okay, to check the seepage or the permeabilities for water supply purposes, for example. Okay, Mark, I hope I have answered your question. Okay, it's not an easy question. Thank you for that. Okay, that's a very good question. Maybe this can be a good question for your project study, I guess. Okay, when you have your fifth year thesis, okay, your uh, yeah, your project study. So that may be a good question to answer. Okay, any other questions? So I do hope I just hope that you understand my lecture, okay? Because you seem to be asking very good questions. Okay, okay, so I guess if there are no more questions, I think we have already exceeded our time. Apologies for that. Okay, so if there are no more questions, so thank you very much and have a nice evening. Okay, so um, you may now leave the chat, the Zoom meeting. Thank you, everyone.